right, in this video, we are going to be looking at optimization problems. Optimization means finding the maximum or minimum of something. There's a lot of geometry concepts in this one, and I know for me, when I was a calculus student, this was one topic that I found really kind of challenging for sure. So I hope to kind of unchallenge it a little bit, but know that visuals are going to be your best friends, labeling is going to be your best friends, and usually we have two equations with two unknowns, and you're going to have to kind of do a system of equations type of thing, okay? So if you go into it knowing, draw a picture if it's not given to you, label things, find the equations you need, and most of the time we'll have two equations with two unknowns. That's kind of the foundation of what's going on here. So let's go ahead and look. There is a problem-solving strategy from the textbook here that I will be using kind of loosely throughout solving these problems. But the first problem here says that a rectangular garden is going to be constructed where one of the sides is going to be a rock wall, and then you're going to use wire fencing for the other three sides. Given 100 feet of wire fencing, what dimensions would create the maximum area, and then what is that area? So remember, the area, right, is like the space that this takes up, and this shape is a rectangle. And so area is going to be length times width. Now this is already labeled for us and to X and Y. So area for this rectangle is whatever X times Y is. Now we want to maximize area. So I want to figure out the maximum area. I'll be finding A prime, but I can't really do that with X and Y. I mean, I guess I could use implicit differentiation, but that's not really going to be helpful here. So remember I said before, two equations, two unknowns. There was another piece of information that's super, super important given in this question, and that is 100 feet of wire fencing. Now the rock wall doesn't count. The wire fencing has to go here, here, and here. So X plus Y plus X must be equal to 100. I'm going to use all of that fencing possible for my garden here, where I know that 2X plus Y equals 100. Now we like taking the derivative of things with respect to X. So let's go ahead and solve this for Y. And just like we would with a system of equations, we're going to plug that in to our equation here so that way I have area now just in terms of X. So area is equal to X times 100 minus 2X, and that's going to be 100X minus 2X squared. Now, if you already know some things about quadratics, you might be looking at this and realizing this is a quadratic that opens down and definitely is going to have a maximum value. You could even look at the zeros. It's going to be at 0 and 50. And if you know things about vertices, you know where that's going to be. So there are some ways you can do this non-calculus wise if you have really good function analysis background, okay, and you're really strong in that area. Let's go ahead and do the calculus part of this though. So I'm going to take the derivative with respect to X here, and I get 100 minus 4X. Now we know that a maximum is going to have a derivative equal to 0. And I can go ahead and solve this and get that X equals 25, which makes sense. And so 25 is going to be the length of these sides, which means 25 and 25 make 50. I have another 50 yards left, so Y is going to be 50 or 50 feet left. If I want to figure out what that maximum area is, I would then plug this in to my equation. I'm going to go ahead and do that in Desmos. So let me pull that up. All right, so I have A of X is 100X minus 2X squared. We could kind of change the window around here just because of what I already know. Let's actually make that just a little bit bigger. And let's make this up to like 400. Oh, that's not even close, right? Like that's not even going to be anywhere. Let's do 4,000. Okay, there we go. And that max is going to be 1250, or you can plug in here A of 25 and it will give you 1250 there as well. And that's going to be in feet squared. All right, let's look at another example. This is a very typical example. So we're going to make an open top box from something that's 24 inches by 36 inches. So we have this piece of cardboard. It's 24 by 36. And we are going to remove a square from each corner and fold up the flaps. Now, if you had me for, by chance, for college algebra or pre-cal, we've done this question. And so this is the like X here, and you're gonna end up making this box that's like open box here. Now, instead of having two equations with two unknowns, this one's a little bit different because we have our 24 and our 36 on our limiting factors here. So that's going to kind of be our second equation. I'll get to that in just a minute. We want to maximize the volume of this box. So let's think about volume is going to be length times width times height. We need to figure out what the length, the width, and the height of this box is. Well, if I'm cutting out these X squares and folding them up, my height is X. Length and width, that's going to be dependent on these pieces here. Now I'm cutting out X on two sides, right? So one of these sides here is 24 minus two of those X's because I'm cutting out an X on each part of that. So 24 minus 2X and then 36 minus 2X. And this is the substitution that we are going to do. So there aren't necessarily two set other equations. The thing that's helping us plug in, so like here, right, we knew area equals length times width right here, and then we were able to then put this in terms of X and Y and then plug in for X. Similar thing here, I know that volume is length times width times height. I now need this all in terms of X, and I need to use the information given to me in order to do so. All right, so length, it doesn't matter which way you plug these in. So if you call this the length and this the width, that's fine. And then a height of X. I'm going to go ahead and just tell you what the final answer is as far as distributing this out, just to kind of save us some time here. And so we end up getting 864x minus 120x squared plus 4x cubed. All right, now I want to maximize that volume, so I'm going to take dv dx, and I'm going to get 864 minus 240x plus 12x squared. Now, 12 is a factor of all of these, and so let's see, what is 864 divided by 12? 72. So I'm going to factor out a 12. I get 72 minus, that's going to be 20. And then if I were to find two numbers that multiply to 72 and add to negative 20, there isn't anything. So I'm going to have to use quadratic formula here. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I realize my quadratic is backwards, but hopefully that's helpful. And I end up getting, let's go ahead again and just pull up our good old pal here. And do plus the square root of 400 minus 4 times 1 times 72. Divide that by 2. And we get about 15.29 as our answer. And then let's see what's 20 minus. Okay. Okay, so let's go ahead and just round to one decimal place. So we'll say 15.3 and then 4.7. And then let's go back up and look at our domain here. Now, if I cut out an x of 15.3, I only have 24 inches here. And I have to cut out 2 sides. So the max I can make x is 12. So 15.3 is not going to end up being a solution. And this is going to be my x value that's going to cause my solution here. Okay. Let's go ahead and look at a graph of volume and just check this out. So I'm going to do it in the factored form. So y equals 24 minus 2x, 36 minus 2x, and then times x. And you'll notice here, let me go ahead and turn off this other function. You'll notice here that I do end up having my derivative equal to 0 in 2 spots. But this is a minimum. Okay, this is when our volume would be a minimum. I don't want that. I want the max volume. And so this is actually the one that I'm looking for right here on my volume equation, the maximum of the volume. All right, we have one final example. I'm going to go ahead and get rid of this writing over on this side to give me a little bit more room. And in this one, we want to look at a rectangle that's inscribed in this ellipse. So here's one of my equations with x's and y's. And I want to know what are the dimensions of the rectangle to maximize the area. Now, this is a little bit tricky because the whole rectangle is what we want to look at. And this point right here, xy, is only this x and this y. But I want this whole area. So my base is 2x and my height is 2y because only one xy only gets me that much, but I need this whole thing. So I need a length of 2 of those x's and a height of 2 of those y's. So area equals 2x times 2y or 4 times xy. All right, let's go ahead and solve this for y. So I get y squared equals 1 minus x squared over 4. And it should make sense that y is equal to plus or minus the square root of this piece here. Now I'm only going to worry about the plus side so that I have a function. And I get 4x times the square root of 1 minus x squared over 4. All right, let's go ahead and take the derivative. I'm going to take this step away that I solved for, so I have room. There we go. All right, and so I need to take the derivative of this with respect to x. So derivative of the first times the second plus the first times the derivative of the second. Okay, and then the derivative of the inside, I'm going to take that down, negative 2x, leave the 4. All right, let's do some canceling. 4's cancel, 2's cancel. I get this 4 square root piece, and then minus 1 over this square root piece. All right, so to save some time, I would multiply this by the square root, and then I'm going to end up having a common denominator with 3 minus x squared in the top once you simplify. This is going to be equal to 0 when x is equal to plus or minus the square root of 3. And so that's